Approximate analysis of indeterminate frames is an important skill in order to develop a sense of the answer before you conduct more detailed analysis that we'll cover in later chapters. In this case, we're going to talk about analysis of frames subjected to vertical loads. And the key concepts we're going to cover are making reasonable assumptions for frames with vertical loads and using equilibrium to find reactions for a frame. Here's our frame. All of the beam column connections are rigid, and the bases of all the columns are fixed supports. We want to determine approximately the support reactions at point B of the frame. And here's our approach. We'll begin by making simplifying assumptions. Since it's an indeterminate frame, equations of equilibrium alone are not enough to find all of the internal loadings. So we make some assumptions that provide the additional pieces of information we'll need. Then we're able to calculate internal loadings at the inflection points. That will be sufficient information so that we can, in step 3, calculate the reactions at point B. Let's get started. Our first step is to make the appropriate simplifying assumptions. And the assumptions we will make are as follows. Since the rigid frame is subjected only to vertical loads, we'll assume, one, that inflection points are created at 10% of the beam span from each rigid connection to a column. An inflection point is a location where the moment is 0, and therefore it'll behave like a hinge. We'll also assume that no axial load is generated in the beams. Now we're ready to implement those assumptions and calculate internal loadings at the inflection points. I specifically choose the inflection points because it's a place where I already know the moment. The moment's 0. So based on our first assumption, our inflection points are 2 in each of the beams. And we'll label them D, E, F, G, H, I, J, and K. The inflection points exist, in this case, 10% of 40 feet is 4 feet in from the end. These two are 4 feet in from the center of the column, and that means that in between the two there's 32 feet left. E and I exist 2 feet from the center of the column. D and H exist 2 feet from the center of the column, and that leaves a 16-foot span in between the inflection points. So now let's draw a free body diagram of piece HI. We have the shear at I, the normal at I, which we know is 0. That was our second assumption. We have the distributed load, 0.5 kips per linear foot. The shear at H, the normal at H, which we know is 0. We know our span is 15 feet. So at some moments about point H, I'll choose clockwise as positive because all of the items not going through point H cause a clockwise rotation. So we have the 0.5 kips per feet over 16 feet gives me the total force, and that resultant acts at 16 feet over 2. We have the shear at I acting through 16 feet. We solve that for the shear at I. We get a negative 4 kips. Now, free body diagram of the piece right below it, DE. We have the shear at E. The normal at E is 0 based on our assumptions. The shear at D. The normal at D again is 0. Applied distributed load of 3 kips per linear foot. We sum moments about point D. Again, I'll choose clockwise as positive because I think it's easier bookkeeping. We have our distributed load, 3 kips per foot through the 16 feet. Oops, we didn't label that. 16 feet. And that resultant acts halfway across. We also have the shear at E acting through 16 feet. When we solve for the shear at E, we get a minus 24 kips. Now let's draw a free body diagram of segment JK. That segment is 32 feet long. We have the shear at K, the normal at K, which by assumption number 2 is 0, the shear at J, and the normal at J, which we know to be 0. And we have our distributed load of 0.5 kips per foot. So we sum moments about point K, choose clockwise as positive. We have the shear at J through 32 feet. Coming back the other way, we have our distributed load acting over 32 feet, acting at 32 feet over 2. That gives us a shear at J of positive 8 kips. Now free body diagram of the segment right below it, FG. Where we have the shear at F, the normal at F that we know to be 0, the distributed load. Notice this is not the same as it was for DE. This is 2 kips per foot. The shear at G, and the normal at G, which we know to be 0. This piece is also 32 feet long. Well, some moments about point G will take positive or we'll take clockwise as positive for our summation. We have the shear at F acting through 32 feet. Coming back the other direction, we have the distributed load acting over 32 feet, with the resultant acting at halfway across the 32 feet. That gives us a shear at inflection point F of positive 32 kips. Step 3. Now we're ready to calculate the reactions at point B. We'll do that by drawing a free body diagram of B, E, F, I, J. And remember, points E and F were the inflection points in the lower beams. I and J were the inflection points in the upper beams. So we draw our free body. With reaction By, Bx, moment about point B. We had the shear at E, which is a negative 24 kips, the normal at E, which is 0, a distributed load of 3 kips per foot over this piece, shear at point I of minus 4 kips, the normal of 0, and this entire top beam segment has a distributed load of 0.5 kips per linear foot. The shear at J is positive 8 kips. The normal at J was 0. Shear at F, positive 32 kips. The normal at F, 0. And the distributed load over this segment of 2 kips per foot. The dimensions are 4 feet on this side, 2 feet on the left side. Now we're ready to apply equilibrium. Let some forces in the x direction. We'll choose to the right as positive. We have the reaction Bx, but notice, because of our assumptions, all of the normals are 0. So our reaction Bx will predict to be 0. Some forces in the y. We have reaction By. Then we have at E a minus 24 kips. At I a minus 4 kips. And then we have the 3 kips per foot distributed load over the 2 feet. The 0.5 kips per foot over the 6 feet. The 8 kip downward load at J. The minus 32 kips. And we run out of room on the end, but don't forget the 2 kip per foot acting over 4 feet right next to point F. Put all those together, we get By is a positive 85 kips in the direction drawn. Now, let's sum moments about point B. Again, we'll choose clockwise as positive. We have the moment reaction at B that we're looking for, to which we'll add the negative 24 at point E, acting through 2 feet, to which we'll add the negative 4 kips, acting through 2 feet, to which we'll subtract the 3 kips per foot, acting over 2 feet, acting at a distance of 2 feet over 2. And coming up to the top, we also have a negative 0.5 kips per foot, acting through 2 feet, acting at a position 2 feet over 2. Then on the right side of the column, we add the effect of the distributed load, 0.5 kips per foot, acting over 4 feet at a position 4 feet over 2. We also add in the effect of the 2 kip per foot distributed load, acting over 4 feet, acting at a position of 4 feet over 2. And we add the 8 kip shear at J, acting through 4 feet, and the 32 kip shear acting at F through a distance of 4 feet. Wow, that's a lot of stuff acting on our free body diagram. When we put all those together, our moment is a negative 117 foot kips. Remember, we drew it clockwise, so the moment reaction is actually counterclockwise. Now let's go back and review. We have a rigid frame subjected to vertical loads, and our problem statement asks that we find the support reactions at B. In order to perform this analysis, we decided to make some simplifying assumptions so that we can get an approximate answer. Our assumptions are the location of inflection points in the beam and that there is no axial load generated in the beams. We then calculated internal loadings at the inflection points. We started with free body diagram of piece HI, where we cut it at the inflection points, then piece DE, JK, and FG, so that when we drew our free body diagram of BEFIJ, we had all forces identified except for the support reactions, BX, BY, and the moment at B. We found that the horizontal reaction, BX, is 0, that the vertical reaction, BY, is 85 kips up, and that the moment reaction, MB, is 117 foot kips in the counterclockwise direction. Well done.